then the momentum of the photon increases and you are creating huge impact to measure the photon and large momentum uncertainty. On the contrary, if you decrease the momentum of the photon, then you take such a large wavelength, then the position becomes very uncertain. But remember what Newton told you, his law will work when you can tell position and momentum both. That is the whole problem. So, since P photon is h by lambda as I showed, delta x, you remember it is uncertainty is what is the wavelength, and uncertainty of the momentum measurement is the momentum of the photon, then you can immediately see from this that this delta x into delta p becomes h, which means if you try to reduce the uncertainty, the error in the value of 1, the other error increases. In no way you can decrease both, and Newton wants both. So in fact it may be shown that minimum uncertainty, actually I have given is the order of magnitude, one can show that the minimum uncertainty that you can produce is delta x delta p is h by 8 pi, where this h by 2 pi I have called h cross. Okay. Now Newton said x and p are independent. So what is the lesson? The lesson is Newton said, let me go back, Newton said x and p are the two independent variables. What quantum mechanics has told you, that the quantum picture brings in relation between their uncertainties.
So how do we know that there's
Who is talking from?
So, sorry to interrupt, but how do we know that there's no other way of measuring these two quantities?
So if you can suggest some way to measure these quantities without interacting with the system, then of course that will bring a new subject in the world of physics. But you have to tell me what the other, you have to without interaction, because the interaction is creating the problem, right? So it's a good question if somebody can create anything like that. So I'll take your question, just let me, I'll take infinite number of questions, no problem. Okay. 2, I mean I have noticed this, I mean just when I was redefining, please it called it h cross by 2, I am sorry, this is cross by 2. So uncertainty in measurement, actually now I told you that see for small objects, so if your object is very large, you create a uncertainty by wavelength, who cares? But an electron which is so small, if you create this amount of uncertainty, that is a huge error, and Newton's law will not work. You are not being able to determine position and momentum. It is a head-on problem, no experiment is needed. It is a problem hidden in Newtonian formulation. So, as all kinematical physical variables I showed you, like energy, angular momentum, depend on position and momentum, I told them two fundamental variables. So their values also become uncertain. So value of energy becomes uncertain, value of angular momentum becomes uncertain, because position and momentum there is uncertainty generated. Why? Because of your way of measurement. So the question that he asked is a beautiful question, that can I without measurement say something? You can say something, but that is not acceptable in science. So this is an error which is not your instrumental error. This is an error, please try to understand, this is an error inbuilt in the nature. You cannot escape. So our knowledge about everything is intrinsically uncertain, and breakdown of Newtonian deterministic law means, which definitely tell me at this time t it is there, now I cannot say this. So let us take a quick small examples. Quantum pendulum. So you learnt, all of you studied how the solution of a pendulum. If you remember, they consider a harmonic oscillator which is p square by twice m plus kxa square by 2, this is the potential, this is the kinetic energy. What is the minimum value of energy if I ask you? Newton will tell you x and p are two independent variables, it can be, it is a positive quantity, this is a positive quantity. So its minimum value can be 0, its minimum value can be 0, its minimum value is 0 classically. So, pendulum standing at the mean position. But what uncertainty has done, they have created a relation between their values. So, according to Newton, this is independent and can have any value, therefore minimum value of E is 0. A classical pendulum may stop. However, uncertainty principle produces a correlation between P and X, because delta X is X and delta P is P, where this is H cross by 2. If you substitute this in this expression, you get this expression for the energy. And then you minimize this to find what is the minimum. And how do you find minimum of a function? You differentiate that function, put that equal to 0. So, you do this, you take del E del X and put that equal to 0. It is a simple calculation. You find that x square is this by putting del E del X equal to 0, and that solution you put back in the expression of energy, and the minimum that you get is half of H cross omega, where omega is root k by m, that I told you earlier. So what you have learned, the minimum value of a quantum pendulum is not 0. A quantum pendulum cannot stop. Why? Because if it stops, its position becomes absolutely certain, and therefore momentum becomes infinitely uncertain. So consider a solid comprising of many molecules, they vibrate about their mean position. The average vibrational energy measured its temperature. All of you know that we have a solid and it's a many molecules are sitting at their point and they are vibrating, and that vibrational energy gives you the temperature of the body. The minimum energy can never be 0, therefore you can never reach the temperature absolute 0. It is coming from quantum mechanics, that you can never have absolute 0 means all the molecules of the solid is static, but you can never have this. See the remarkable consequences that are emerging from this uncertainty principle. Consider the hydrogen atom. Energy of an electron is this. Now minimum of the first term is 0, of course, because this is positive, and minimum of this term is the second term becomes smaller and smaller. This is a negative term behind it. As r goes to 0, this becomes more and more bigger, but minus bigger means it is becoming smaller. So as r goes to 0, it becoming smaller and smaller, therefore the electron should collapse into the nucleus, that is r goes to 0 means it is going to the nucleus. The electron collapses into the nucleus, which it should do because of losing energy through radiation. All of you know that it should spiral down to this. But Niels Bohr told you that for some unknown reason, nobody knows, there are some stationary orbits. All of you have studied in your school days that angular momentum it at integral multiple of h by 2 pi and so forth. But let us see what this quantum theory tells you. But this does not happen. Why? Because according to uncertainty principle, del r del p, now this the measurement of position and momentum is h cross by 2, take del r equal to r, del p equal to p as we did and substitute it here, and you can just rewrite this as this, and the minimum value of energy, this is a constant, so minimum value of energy will be when this is equal to 0, this is equal to 0, and from this you calculate r, you get the first Bohr radius which is 53 picometer for the equilibrium state. So you can estimate that the electron will be in a not at the 0, but at some finite distance, which is the radius of the first radius of the electron, and the energy is this one, which is exactly that 13.6 electron volt, that is the energy of the first orbit, n equal to 1 orbit. You know, you have studied this, that in Bohr's theory this is the first orbit where it rotates. So we find that this quantum understanding and the uncertainty principle give us some beautiful results, and the root cause is that our inability to determine position and momentum simultaneously. And now we understand why we can't do this. So Max Planck and de Broglie, they some two big names. So the important experiments in this context were electrons which are known to be particle like, we all thought electron is a particle, behaves like a wave in an interference experiment. So do instead of light, throw electrons in a double slit experiment, all of you have studied, it produces wave like character. Many electrons here, no electrons there, then many electrons here, so it forms a band structure. On the other hand, light, which you always knew to be a wave, behaves like a stream of particle called photons in photoelectric emission when light falls on a metal. So actually our world, that this is wave, this is particle, everything is getting completely confused. But now we have started understanding that the root cause is the uncertainty principle. So let me try to explain the exact meaning. So this dual nature is related as this P equal to h by lambda, where h is Planck's constant. So meaning of wave particle duality, this what is actually, we know when I was a student I always become very intrigued that what is this wave particle duality. So I understand something is going on like this, but then I understood that there is an uncertainty measurement that is creating some uncertainty, but still what this wave, exactly what kind of wave it is. So now I will try to explain. Common sense understand, suppose I ask you what is a particle, you will say system confined in a very small region is called a particle. It is roughly our common sense idea that this is here, it is a particle. It is very confined at a point, so I can write its position as x as a function of t. On the contrary, wave is distributed over a wide region in space, right. Where I use that, you have seen the picture of waves where it is like this, is distributed all over the space. So it is we write it as a function of x and t. It is the amplitude of the disturbance of the wave at different x at different time. So let me give you an example. All of you have studied simple harmonic wave, it is distributed like this. It is uniformly distributed wave all over the space. So it is going from here and uniformly distributed. Now its equation, all of you know, you have seen wave equation is given by this. So such a wave represent a particle whose position is spread all over the space. Suppose I say my particle, that electron is given by this wave, this is amount telling me that its position that you are trying to describe is spread all over the space, because this wave is spreading all over the space. But its momentum is fixed because it is a fixed wavelength, and therefore its momentum is fixed and fixed energy equal to h nu. So this wave represents a particle whose position is infinitely uncertain. I do not know where it is spread all over the space, but its momentum is absolutely fixed. So it is satisfying my uncertainty principle. One is 0, other is infinity. But now suppose, so del x is here infinity, del p is 0, therefore you can see del x del p, you can calculate, is equal to h, condition is satisfied. Del p equal to 0, del x equal to h by del phi infinity, spread all over the space. Now but if we superpose, suppose I now take waves from lambda to some another spread of wavelength lambda plus delta lambda and superpose them. That means it implies that the momentum, the wave that is describing your particle, its momentum become uncertain from p to p plus delta p, because for every lambda there is a p. So I have introduced from lambda by hp some momentum, right. So now that wave represents a particle whose momentum now becomes uncertain by delta p. So new position uncertainty will be h by delta p. Now delta p is not 0, it is not a fixed momentum because I have superposed different waves. And let me check what is the result. Do you know what is the result? The result is something like this. So when I have superposed waves, see in one region the x becomes, the amplitude becomes very large. So what is your only possibility of interpreting this wave? The only possibility is telling that this wave represents probability. See, you have no other option, because now you can say that when I am making my position momentum little bit uncertain, position is becoming more and more, position is becoming more and more certain. It is now getting more and more localized. In that region it is confined. Previously it was spread all over the space. Now the position is becoming very sharp here. So now I understand that, okay, so as delta p increases, delta is becoming smaller and looks more like localized with less uncertainty in x. It is called wave packet. a wave packet looks more localized, looks like a more localized system, right. So, I can say that whenever a quantity we cannot determine exactly, this Newton already you have understood, because of our experimental disturbance we are creating uncertainty. Whenever there is an uncertainty, where lack of uncertainty, we describe it statistically by chance or probability. Remember, why do you say chance of getting a toss in the top, head is half, tail is half in a coin toss? Why? Because you do not know what is going to come. Whenever the outcome is uncertain, we invoke statistics. So here, since this experimental disturbance leading to uncertainty principle that we have shown, we have no other choice but to bring in statistical description. What statistical description? That, so interpret the wave function for the system as a chance function or probability function for the system in space. So I can now say that this is a good way to understand, because when previously it was this position was absolutely uncertain, is spread all over, the momentum was absolutely certain because that fixed p, fixed lambda. Now as I superimpose many lambdas, the momentum becomes uncertain, but then position becomes little more certain. So what this gives? So if I say this is the probability, so previously probability was same everywhere, so the particle is equally probable to be everywhere. So what is this uncertainty? Infinity. But now I can say that the particle is more probable to be within this region, then it is becoming more and more certain. But in the process, momentum has become little uncertain, but del x del p is h. So earlier Newtonian mechanics gave how the position of the particle evolves deterministically at various time x equal to xt. This was Newton's equation, remember we solved it, the 2 integration constant by that initial condition. But now quantum mechanics describes the position of a system with probability function psi xt and gives how this probability function evolves with time. That is, suppose the probability function is this, so particle is most probably here. Now it has, after that time it is here, so probability of getting it here. You are not saying the particle is there, particles can be anywhere, but the probability of getting it more here, and that changes with time. So that evolution of the probability is given by Schrödinger equation. That is the equation which replaces Newton's equation. So now we have a picture emerging from this, a picture of dynamics of probability. So that is quantum mechanics, and we had no option because the uncertainty is inherent in nature. It is not that by making more and more accurate instrument you can make both x and p certain, you cannot. One is related to the other. So this is Schrödinger equation. Don't worry too much about this because this equation looks a little more complicated, but see these are probability, how the probability function varies with space and time. It is a wave equation or Schrödinger equation and written in 2 forms. That is not important at this stage, but you just try to see that Newton's deterministic law, mass into acceleration from when you get x as a function of t, we write this equation, we solve it to get psi as a function of xt, that is how the probability is changing. So this wave, the word wave particle duality, this wave is a probability wave. That wave is actually represents the probability how the system is distributed. Now deterministic description of Newton's law is no more valid due to inherent uncertainty in the process of measurement and is replaced by probabilistic description through Schrödinger equation. Now just 2 more comments. From Schrödinger equation it can be shown that just by this equation you do a little bit of mathematics, nothing more than that, do a little bit of mathematics, you can show the summation, or basically it is an integration of these quantities 1. Now you see you will identify that not psi, but this quantity actually represents the probability, because when you sum over all x and this is giving you 1, that means if this is the probability of getting the system at x equal to some value, and if you integrate over whole infinite value, it has to be equal to 1, because total probability has to be 1, right? If this particle is here or there, you taking the sum, the total probability. What is the probability of after a coin toss, either it is head or it is a tail, total sum is 1, right? So here, therefore I say this indicates that psi x star, psi, this is called mod star. This is nothing but psi complex conjugate times psi. All of you know complex numbers, so it's a complex conjugate times psi. These can be identified as the probability of the finding the system between x and x plus dx at time t. So when we solve Schrödinger equation, we find psi, calculate mod psi square, and we say this is the nature of the wave, probability wave, and here the particle is most probable, here less probable, here more less, but total sum is 1. So this gives us, lead us naturally to this definition and identification. So there are some great masters in this, you know, you have heard all about these people, but then I make the one, how much time do I have?
5 minutes.
5 minutes. Now see one interesting thing, we have shown mod psi squared dx equal to 1 indicates that the system, say particle, will always be there somewhere in space, of course, because if it is at x is some value psi square and sum over all x from minus infinity to plus infinity in the whole space, then obviously it is somewhere and it is giving you 1, but it is telling you something more. It is telling you that it can never be created or destroyed. Now suppose a particle is now here, after some time it is destroyed, then the probability should not be equal to 1, this is gone. So it is telling you that this particle we are talking about can nothing be created or destroyed, but you know later that experiment showed creation and destruction of particle in high energy collision. When particles come and at a very high energy hits each other, new particles are created, or some particle which was there, it decays into some other particles. So this constantly happens. What will happen with those particles? Because for those particle probability of this now it is something, and after some time the particle is not there. So how will you handle this in this case? So yes.
I guess if a particle is made out of multiple other particles, maybe we could, sort of consider it as. So for particles made out of multiple particles, maybe we should consider those particles as independent even if they are combined into one of them.
No, just let me tell you what happens, that it is not that that particle is made of this particle. It is not that. It is not that it is a composite particle created. Though when the decay process creates two completely new particles. It is not that one particle, it is a composite nature. Suppose two of you are holding hand and you are, it is not that. So I will tell you the answer. Listen and then I will take your question. Just hold on. But experiment shows creation and destruction of particle in high energy decay. Why it happened? How then we handle this? Newtonian mechanics assumes mass and energy conservation independently. Energy is conserved and mass is conserved. All of you are studying Newtonian equation. But all of you know that when Einstein developed special relativity by changing the Newtonian concept of time, I told you that I don't have time today to describe that. But what he found, the conversion of energy into mass leading to total mass energy conservation together. So Einstein theory, which is a completely new theory which I told you, is another variation from Newtonian mechanics which comes from a new interpretation of the coordinate time. That is a very interesting theory which shows that mass and energy are not independently conserved, but they are conserved together. So interconversion is allowed. So when such a thing happens, some energy is converted into mass and new particles are created. But you may say, but then my Schrödinger equation is unable to describe that. It is unable to describe because Schrödinger equation did not consider relativity the way you have written. So it is not giving you anything. So then what, how to handle that? It is describing very successfully, but only non-relativistic particles. But when you consider relativity, when particles are moving at a very high speed, then this quantum mechanics will start failing, and quantum mechanics will be modified little more. That modification I do not have opportunity to explain you in this class, but that special relativity plus quantum mechanics together form what is called relativistic quantum field theory. Yes, yeah.
Sorry, sir. I had one last question.
Yeah.
Regarding the uncertainty principle, does it simply prove that there is no way to precisely determine both variables in a specific system of measurement, or does it prove that there is no system of measurement that allows both
There
to
is
be
no system of
precisely
measurement, we can
determined?
determine them simultaneously. No system of measurement.
How
So
did
if you
he
know,
prove
I mean,
that,
it
sir?
doesn't prove that. What you have to do, you have to come up, you have to imagine that when you measure position and momentum, how do we do this? Just think about it. I mean, we casually say, okay, we measure the position is there. Just ask yourself that when I make this statement, what I exactly mean? How do you make the measurement of position? Think about this. Experimentalists do that, right? We can always say that we are measuring momentum, we are measuring energy, we are measuring. How do you do the measurement? And when you think about it, you will see the measurement needs a kind of interaction with some interacting process. The process inherently creates this disturbance. You have no control on that. So if you can come up with some alternative, I will definitely take your question. We will take your solution, right?
So, sir, you simply have to go through all possibilities and see, and you will find that none will work.
Well, you have to tell me some possibilities where you can show an exception, right? So it is true, absolutely true. I mean, so see, when suppose the Einstein, if he didn't formulate the special relativity, suppose consider the situation, only the Schrödinger equation that I wrote is there. Suddenly we see creation and destruction of particle. So we will say this is validating this, right? So you have to then formulate, come up with new ideas, right? So if you can come up with new ideas to contradict this, of course this will be well taken. So we will try to rethink that. I mean, there are certain ideas which some people do not believe in this intrinsic uncertainty, and Einstein himself was one of that such a person. But that as at a different sense, not in the usual sense, he completely believed quantum mechanics. So special relativity plus quantum mechanics, which is called relativistic quantum field theory. I am sorry that I have no time to, or I mean, this is little advanced thing which you will definitely learn soon, but this is the most successful theory of nature so far, which takes care of all the fast moving particle and all the microscopic particles. So what is the lesson that we learned? We learned that we learned Newtonian mechanics very nicely. All of you have learned Newtonian mechanics. You thought that you didn't probably realize that it assumes position and momentum both needs to be determined at t equal to some time simultaneously. That was the inherent assumption, and then everything was perfect. Then we encountered systems like microscopic particles where this is not possible. Why? Because our process of measurement creates uncertainty, and that led to this discovery of this subject, quantum mechanics. And then so many new, as I told you, this evolution takes place. It is not possible to tell you everything, but this is the heart of quantum theory. This is the heart of quantum mechanics. And Schrödinger equation, we are forced from a deterministic description x as a function of time to probability function psi xt as a function of position and time, that what is the probability of finding in this. So when I go from here to outside through this door, you know my path, but when an electron goes, what does it do? At every point a path's position is exactly determined, that is not allowed. So an electron moves through a fuzzy path. Actually it is, you cannot say that it is actually travelling from this point to this point. So our entire picture of the world. So you have seen in your book, when they write orbits, they like electron cloud. This cloud is a description of that probability distribution. So the wave is a description of that probability distribution. So we are forced to think in a statistical way from a deterministic way, and this it is not that it is our inability to do something, so we can improve our everything and fix this uncertainty. No, this uncertainty is correlated. Position and momentum, two fundamental independent variables that Newton thought, they gets correlated, and that completely creates this entire problem. But now fortunately we can determine a probability function which satisfy an equation. So there is some kind of statistical determination at least. It is not that It is behaving randomly. It is not some statistical distribution, and that is what Schrödinger equation, which replaces Newton's law. Okay, so this is the heart of quantum mechanics. So I am now open to question from all of you. Okay. Yeah.
The student first. No, students.
So one doubt.
Yeah.
Can students ask questions in Hindi?
Yeah, sure. I'll try to understand. Yeah, I believe that I will be able to understand. Sure.
So, and even if it is Telugu, then I know little bit Telugu. I can translate it.
Translate it for me.
Yeah.
Okay, sure. Yeah.
In terms of light-matter interaction.
Right.
She asked a question, can we avoid light-matter interactions and address answer?
So you see, you see the. So okay, I am answering your question.
Student does not ask a question, I would like to say.
Yeah, sure. Huh. Any question?
Yes, please don't hesitate to ask questions. These professors are very chill. I am enjoying their talk. I encourage you to please ask questions. Are you understanding? I
Yeah.
hope they will give you the best answers.
Can we conclusively prove whether or not there is a way to determine both
No,
variables?
we can't conclusively prove anything. What we can tell you that see when we, okay, so let me just try to answer whatever be our available knowledge. That when we extract knowledge about something, what we do, so in nature there are four forces, right? Gravitational force, electromagnetic force, and the two nuclear forces. Now both the nuclear forces are very short range force. They cannot be extended at a long distance. The only two known forces that we have are electromagnetic force and gravitational force, and therefore both of them produces the corresponding waves. One was electromagnetic wave, which we know for a long time, and the other is the gravitational wave, which we have detected very recently. But in both these cases, so now you can, another alternative way that you throw a gravitational wave on something, have a gravitational interaction, and then you try to measure something, which we are doing, because it's called the gravitational spectroscopy nowadays. Now gravitational wave spectroscopy or electromagnetic wave spectroscopy, which is light or X-ray or gamma ray, whatever you do, in both these cases you create disturbance and uncertainty. Now if you can think of interacting with something which is neither of this, then we have to think that this process of interaction is not creating any disturbance, whether it is feasible or not. So it is not that we are proving anything conclusively, because that is the beautiful part of science. When Newton's law was at its peak of success, or any other theories, then after some time we find that nature gives us some observation which proves that those are not completely correct. So I am not claiming anything. Science never proclaims that it is this and it cannot be anything else. But what I would like to tell you, with our available way of getting information about some determining variables of a system, these are the available ways, and in each cases you create interaction and disturb the system. Yeah.
You asked a very interesting question. The answer is you can never be sure of any law. Why? Supposing Newton's law is there, my name is Mani. If it is Krishna, how do you know the Newton's law is right? You don't. You have to verify by naming me as Krishna and then proceed. This way, if I raise my right hand, is it? So there is infinite possibilities of answer. So we know, okay, up till now, as he pointed out, there, he has written so far. Tomorrow when it changes, we have to change the law. No single law is valid that way. So this is the answer. We have to learn, as Feynman pointed out, what does physics teach you? You should be able to say, I do not know.
Yeah.
That is
a very, I think one of the greatest lesson, absolutely. That is the great lesson.
The second, yeah, you have something to say? All right.
No.
The second thing is, he pointed out something very interesting in his marvelous talk. He talked about various dimensions of energy and so on. There is one more thing which I'm sure you would have added had the time. there is something called the fine structure constant.
Yeah.
And that is a dimensionless quantity. You should learn how to use that to your advantage. Take energy of an hydrogen atom. In hydrogen atom, it is non-relativistic. So, velocity of light should not enter. Take energy. Energy is mc squared. I have to eliminate c squared. The fine structure constant contains c in the denominator. So, it is mc squared alpha squared, and it is bound state, it will have minus energy. And then you divide by 2. With this, you can calculate many things. If you remember, fine structure constant is about 1 by 137. It is a very useful method of making sure where you are. In physics, it's very important to know whether you are dealing with an elephant or an ant. Then you can make the appropriate approximations. So first thing the experts do is get an idea in which area of the parameters they are in. So these are the two remarks.
Yeah. I just like to add to his very, very valuable comments. Let me tell you, please try to understand, science never proves some kind of absolute truth. Try to understand. Do you think that after this entire discussion I am trying to say that what Newton did was useless or wrong? Absolutely no. We create models. So each are models. So this model works up to this point, and beyond the point we see from some microscopic particle this model is not working. So you take another model. So this is quantum mechanics. So someday it is possible that in some domain you will see that what the quantum mechanics is not working. Then you develop another model, which is what is truth? No question, there is no question of truth. That we are just trying to develop models. When Newton's law formulated his law of gravitation, it was a nice model explaining planetary motion. But when you go to the theory near a black hole, it doesn't work. You need another gravitational model by Einstein. So the thing is, that is exactly what science is teaching us, that we try to develop some theoretical structure or models with which we try to explain as much as possible. That is the goal of science. Okay? So,
Sir,
yes.
I have a doubt.
Yeah.
The position and momentum, whatever error is you have explained, it is very small. Practically, where does it matter?
So see, when suppose my size is, my dimension is 0.1 centimeter, suppose, and you make an error in my measurement which is 0.1 centimeter. It is very serious. It's a 100% error you are creating. So you cannot neglect that. But if my size is 10 meter and you can make an error of 0.1 centimeter, and if your calculation that you want to do from me, they are not sensitive to that place of decimal, then you can say that in my calculation this theory is not required. So if you apply Newton's law to solve the motion of a cricket ball, you can do it. Of course you can do it, and you can see a difference in answer, but the difference comes after say 20 place of decimal. The question is, do you want it or not? That's the whole thing. Quantum mechanics in that sense gives you a better result, but that better result whether it is relevant.
Okay.
Okay, I think we'll stop here.
Yeah, okay, sure.
Out of time.
Yeah,
So
sure.
last question.
Yeah,
It's
yeah.
necessary for everyone.
Yeah.
Can you suggest some very good books for the beginners who want to learn quantum mechanics?
Well,
for school
this-
students,
this-
from where
you
they can start,
I can
start their
suggest
journey.
you one book that is reasonable. It is called, this book is called Concepts of Physics by Arthur Beiser. That book in the quantum theory chapter tells correct, not anything incorrect. So the problem is that in various books you get wrong things written. So you should be careful about that. Beiser's book is good. It's called Concepts of Modern Physics, and there is a chapter on quantum theory. That is good. That's a good book. But of course there are much better books, but for which little bit of knowledge in quantum theory is required. I will ask them to read, which is difficult. Be careful. Don't think that you will read and immediately learn it. Feynman Lectures of Physics, 3rd volume 3. Read the first 2 chapters. It will give an incredible understanding of the subject. Yeah.
Sir, as you had said,
Please.
Venkataraman's books.
Which one? Venkataraman's book. Right. Right. Venkataraman's series of books. That books are very good. Right. Exactly. Yeah.
So, as you had said that when we observe an electron, there is a probability that it can be anywhere. So, for example, we are looking at something very far away. It will look like a point mass. So, can we say the same?
No,
for
you
that?
are dealing with some, say, suppose you are dealing with the point mass. So, you try to understand when you write Newton's law, m d2x dt squared is equal to force, right? That is what you write. Now, what is that x? X is a point in your space, right? Or r vector is a point in your space. So, actually when you write Newton's law first, you write for a point mass, which has no dimension, right? So, it is a very ideal thing. So, when you apply Newton's law for a large object, you take a summation. So, whether it is near or it is far, after all it is a point mass, right? So, what I am finding, so what is the probability of seeing that point mass of or getting that point mass at x equal to say 50 kilometer from me. So, that is the way I say. If you tell me where the electron is, that is not the question. Question is what is the probability of. So, one important question answer in this question context, when you talk about probability, you do not talk about a single experiment, right? So, when you say probability of getting a head is half, what do you mean? The two tosses, one is half, one is tail? No, it is a very large number of experiment. So, when we are talking about this probability picture, in the back of our mind, we have an ensemble of large number of electrons. If you do an experiment on them simultaneously, keeping all other macroscopic condition unchanged, then the probability of here it is say 1/3. That means if you do a very large number of say million of system, then 1/3 will be electron will be seen here with this value. So, this way it's called a wave. So, probability of wave is not a single electron, actually it is an ensemble of electrons.
So, sir, like
You have to, sorry,
So
I
in
mean,
the
can
best
you,
interest of time, see, two speakers of today afternoon session, they have to catch flight.
so can you just share my email address with all of them?
Sure,
You
yes,
are
yes.
most welcome to ask me questions through email, and I promise you I will answer. I always do that wherever I go. Every day I receive so many questions, I meticulously reply. So, please without hesitation ask me whatever questions are coming to your mind.
Okay. Thank you sir for a wonderful talk. Let us thank the speaker once again with a round of applause.
Alright, so now we move to our next distinguished lecture. It is my pleasure to introduce.
Yes.
This one I can take it here.
Okay.
Alert you around 20 minutes or so. 25.
25. That's
I
fine.
think 25.
May I please invite Professor Parthsarathy Majumdar for his talk.
Okay.
So next speaker is Professor Parthsarathy Majumdar. He is a professor at Indian Association for Cultivation of Sciences. He will begin his talk now.
Thank you. Thank you very much. Can you hear me at the back? At the back? Last row, can you hear me? Then I would assume that all of you in the front can hear me. Now, right. So I must begin with an apology that this is not like the last talk, which was on quantum mechanics. And my reason for choosing this topic is because this is a topic about now, whereas the talk you heard before, very, very important for those of you who want to study physics. However, it dates back 100 years. The uncertainty principle was discovered slightly longer than 100 years ago. So what I want to talk about today has some relations to quantum mechanics, but it's about a crisis that we are all facing. That's Mother Earth, our common mother. And this picture was taken in 1968 in a spacecraft where, for the first time, the spacecraft was reconnaissing the surface of the moon. Can I have the lights on, please? Is it possible? Because I want to see the faces. Yes. So they were reconnaissing the surface of the moon so that Apollo 11, this was Apollo 8, Apollo 11 could land there safely. They were doing a recce, as you say nowadays. And suddenly, Bill Anders, who was an astronomer, noticed this picture. remarkable picture. The first time in the history of mankind, human beings in space were observing our common mother, our common home where we all live, and how beautiful she is. Look at her. That's where we all live. She is beautiful, and yet she's also very delicate. She's fragile. And therefore it is absolutely impossible for us not to do anything, well, not to indulge in doing anything which will create a problem for her. But we've already done it. We've done it, and we're doing it. Every time you throw a switch, you're doing it. So we are all sinners, we're all polluters. How are you doing it? Well, when you turn on a switch, what happens is, here is what is called a thermal power plant. I don't know where here, from here, the thermal power plants are located. You would know that better, but you know what's happening there. You're burning coal, and you're turning a turbine, and that is generating electricity. So if you turn on a switch, like you would do to turn on the lights in this room, you're generating a little more electricity, you're burning a little more coal, and you're creating this awful smoke. Look at what it does here. You can't even see what's happening here. That's a smog, it's not fog. It's human created. What does it do? What's the problem? So we have a little smog. Well, you know, we are not going to be around for too long. I mean, I am fairly old, very old, maybe 120. I don't know how much old I am. But you are guys are going to be around. And in order to be around safe and sound, you must be able to breathe. Breathe pure air. Does that look like pure air to you? It's happening now. Go out. Come to my city, Kolkata, or go to Delhi, even worse. What does it do? What's wrong with pollution? There we are. This is the polar areas. The ice is breaking down because the air has warmed up because of pollution. A warmer air would mean that the ice caps are melting. The sea levels would rise. Of course, Hyderabad does not have a big river, but in Kolkata we live near the Ganga. We call it Ganga, but it's actually Hooghly. And there, if the sea rises, I live very close to it, the river rises, and my house is going to get flooded. Eventually, we'll have to learn how to live underwater like a fish. So, learning quantum mechanics is great, but what if you can't breathe? Then we have this one, flooding, like I mentioned. These are from Europe, where they've not seen a flood for huge lengths of time. And this is also Europe and the United States and Canada. In Canada especially, where temperatures were always low, 20-something, suddenly it went up to 50 degrees Celsius. And they had these horrible fires. And they didn't know what to do. Okay? We don't know how to handle natural disasters of this kind. And it's happened already in India. It's happened because of landslides in various places, which used to be very stable. I don't want to get into all those details, but I want to tell you about an alternative. Can we survive? Now, this I know you read as part of your curriculum in high schools called environmental education, but that of course is the most boring topic. I mean, Heisenberg uncertainty is so much more interesting, right? No, it's not. It's boring because the facts are not known to you and the solution is not explored. So here we are. How much energy do we need? Oops, I'm sorry. This is how much energy we demand and how much there is supply. So if you can look at these figures, you can see that this is 10 to the power of 8. This is what sunlight gives us, and this is 10 to the power of 5. So we receive per year, which you can translate per day, 1,000 times more energy from the sun than we make use of. and yet we say there's an energy crisis. Similarly here is another calculation. Now why the sun? Well, we realize that we must have something which is common to everybody. No rich and poor thing here. And the sun, the solar energy, is the only form of energy which is available to you right now. Just step outside. But you say, oh my God, it's so hot. That's all you can say, right? Are we being smart? I mean, it's freely accessible and it's unlimited. How long? 10 years, 20 years? 10 lakh crore years. Yes, please, you have a question.
I'm pretty sure it's about 9 billion.
Sorry?
9 billion.
Billion, million, who cares? Do you really care how many years it is? I mean, for your age or mine, a million is like 1,000, right? It's the same, right? Now, so we have this primary resource which is ours. Now, can you claim that, oh, this coal is mine, or that oil is mine, or that nuclear is mine, or the hydroelectric is mine? No, you can't. To develop them requires enormous government or corporate effort. But your sunshine is yours. Make use of it. Be smart. And it's pollution free. The sun is giving, you're not taking. You are in fact using horrible things to create energy. The other thing I want to tell you is that, usual electric transmission, again you have to just step outside, you will see lots of these transmission towers. Now, I don't think you have an idea what percentage of the electricity generated actually reaches us. It's like 50%. The other 50% is lost in transmission. Transmission is very inefficient. But why do we, yes, please.
Sorry to interrupt, sir, but if I'm not mistaken, even the most efficient solar cells don't use...
Wait. Have I talked about solar cells?
No, sir, but...
I'm talking about the transmission efficiency of transmission towers. When I come to solar cells, okay, so since you've raised the question, I might as well answer it. Let's look at the concept of efficiency. What does efficiency mean? Efficiency means how much you put in, how much you get out, versus how much you put in. That's the ratio of efficiency, of energy, of money, of anything. The same quantity, it has to be a ratio. Now, I already mentioned that the sun is an unlimited resource. So even if you use it maximally inefficiently, how do you care? Right? The question of efficiency arises when the raw material is sparse, when you don't have enough of it. When you have too much of it, too much that you're complaining all the time, oh, it's so hot. That's the only complaint you have about sunshine. Does it make sense? So I guess the efficiency of a solar panel, I don't really care at all. It's how much I can use it. It's how much I can help Mother Earth survive. Okay? So the philosophy of controlling something very efficiently has to do with how much resource you have at the very beginning. Is that clear now? Yeah. So that's what I'm trying to say. And it's easy to learn how to use it yourself. You see, every other form of energy requires some expert help. You need some really big expert technician to connect your lights to the mains, or the mains to a nuclear facility if you want nuclear power, so forth. It's always expert help you need. And long periods of training are required to master this expertise. This doesn't need so. And I'm going to show you how. Okay? Oops, sorry. So the question is, why aren't we using it? That's the big question. Apart from saying that human beings tend to be maximally stupid, even though some of them discovered the Heisenberg uncertainty principle, like Heisenberg did. We don't use it because we are continuously told that, oh, fossil fuels are so beautiful. This is called propaganda. Because you're young people, I must tell you that you have to cut through the propaganda and get to the truth. In very advanced country known as the United States of America, they're trying to say that there is no climate crisis, and yet California is burning and Texas is flooding. These are facts you can check. Okay? So I think you have to be careful. There are mafia, dangerous people. All they want is your money. They don't care about whether your children or grandchildren can breathe or not. Okay? Now I have to tell you a little bit about history and keep a watch on the clock. As Chairman Sir said that I have to finish in half an hour. I'll try to do that. There was this very smart man, very smart, George Cove. He was a Canadian by birth, but he lived in New York, and he developed the first ever solar panels. Now, they were not like the solar panels of today, which are based on materials known as semiconductors. They do not follow the quantum mechanism which today's solar panels work on. But what they did was remarkable, what he did. He used an effect in physics known as the Seebeck effect. And with that, I don't want to get into the details too much because I have to tell you about other things. He made these panels, which look pretty much like today's panels if you look at them. But what happened to him? Now again, history has this problem. So we are talking about 100 and something years, 150 years, sorry, how much is it? 110 years back, 115 years back. And what really happened, we don't know. So we have to piece the information together from the sources of history. And this lady, known as Sugandha Srivastava at Oxford University, did that for us. And what did she say? Well, it was definitely viable, and George Cove's solar panels were getting to be very popular in New York. But then, at that time, the big businessmen dealing with fossil fuels, they were very worried. What did they do? They kidnapped the poor guy and threw him somewhere. And he was financially incarcerated. All his money was taken and his business collapsed. Now, if this is true, then you can blame the fossil fuel people that they're absolutely responsible for 40 years of global warming, the ozone hole, and the corresponding environmental destruction. So we have to remember that we are not the only inhabitants of Mother Earth. We have to remember that. We can't be human-centered. And the greatest thing there is that they just ignore climate change if there is profit, there's money in it. Now, I'm saying some things which may sound a bit political, but you don't have to believe me. Check the facts. Nobel Prizes have been given calculating the effect of climatic destruction. Nobel Prizes. Again, I can share all this information with you, but I don't have too much time. So what I'll do is I'll talk about the worst offenders. I don't have to, I think all of you will agree with me to say that we must stop wars right away. And there are 2 wars going on. I mean, okay, when I wrote this transparency, Israel was still committing genocide in Gaza, and Russia was committing genocide in Ukraine. And some other places were committing genocide, like Sudan, which I don't have the facts, so I didn't write it, but Sudan also is a I read it in the newspaper. You already have a bad, air quality index, and Diwali bursting firecrackers make it only worse. I mean, that's not very smart, is it? But then they are burning millions of firecrackers. Firecrackers are nothing. The energy emitted is nothing compared to the armaments they're using. The second one has to do with freight transport. Now, you may be happy that something which comes out in the United States, like an iPhone, will be available at your markets tomorrow, thanks to air freight. Is it good? No, it's terrible. Do you need it? Maybe you want an iPhone, but can't you wait for a month? Can't you not have an iPhone? So you can ask all these questions. The human greed for stuff is making sure that there's an enormous freight industry all over the world. Finally, I come to something which will touch a nerve, because everybody is talking so much about it. It's called artificial intelligence. Now, you will say, look at this Buddha. He's how good artificial intelligence is. So why am I against it? Am I an idiot? Do I not realize the good qualities that artificial intelligence might do? But the problem with science and its application in technology is that you always get a double-edged sword. You solve one problem with one edge, and from the other edge, different problems arise. It's so strange, and that only shows the limitation of things we make. It's our own limitations. We can't create anything which has no problems. The problem with AI, I don't know how many of you are aware, is that you need a 24/7 processing unit of gigantic dimensions. Why? Look, this thing has to obey everybody's questions and answer them. How much data would that require? If you think of the amount of data that is used to train an artificial intelligence platform like ChatGPT or Gemini, it's just mind-boggling. To be able to do that so that you get an instant answer when you ask a question on the internet, these processors have to run all the time. What do they run on? What do they run on? Fossil fuels. Back again. Okay? So the fossil fuel doesn't have to worry about you and me. More and more artificial intelligence platforms would mean more and more consumption of fossil fuels. That's it. So that is why I think they're very cynical destruction of the environment, of all animals, all species of living creatures being able to breathe. Okay? I mean, there is calculation of how many species of living creatures are killed by global warming. There are calculations available. Now, why should I kill this poor creature who has not done any harm to me? Just because some fossil fuel mafia wants profit? This is weird. I mean, to think about it is so weird. What about other clean energy? Well, hydroelectricity, I don't know. Do you have hydroelectricity in Telangana?
Yes.
You do? Okay. But it's somewhere far away, right?
Yeah, about 200.
Yeah, so if you want power from there, you're back to the transmission problem, and you're back to the loss of efficiency of energy. So that's the problem with hydroelectricity. It's clean, but also needs a gigantic investment from a corporation or government. Nuclear energy. Now, the less I said about this, the better it is, because it's, please let me complete my sentence, then you can raise your hand, right? You have to wait for me to complete my sentence. Nuclear energy, we have a very, very poor record. I don't know, maybe I should ask you now the question since you raised your hand. Do you know what percentage of India's electricity demands comes from nuclear? Any idea? No idea. I'll tell you, it's 3%. And after so many years of nuclear reactors and so on. So I don't know, I don't want to say that we have blown it. Of course, there are countries like Canada and France who have done exceptionally well with nuclear, but they also have problems. One problem is, of course, a serious issue of nuclear waste disposal. It's a very, very serious issue. If you have a little bit of radioactivity here, you can say goodbye to this old man, because I'll be in a hospital very quickly. The other is also that you need a huge amount of investment. And the third is this problem of transmission. You can't live inside a nuclear reactor. So the nuclear energy has to be used to convert it to be electrical energy, and that has again to be transmitted through transmission towers. So you're back to the problem. So you see, you have to imagine these things in their totality. Wind energy is the best apart from solar. But again, there are issues. I don't know of windy places in Telangana, but I know of windy places near coastal Andhra. There's a lot of wind. So there you can put them up. But I probably should not put this in red. But look at sunlight. If you have a little device, just imagine, in which you can use your sunlight and convert it into those little, what do they call them? Cycles, but those are cycles which travel by electricity. They use batteries. But if you can use solar to charge batteries, you can go from there to there in a zippy, quickly. 5 minutes? But I only took 20. Okay, no problem. I'll show you pictures. But let me just go through this. Can you give me 2 more minutes? Because let me make a deal with you, sir. I'll finish at 4. Okay? I mean, with all the questions and so on. So I'll finish my talk, and then by 4, I'm out of this room. Okay? So here we are. This is a basic mechanism of how a solar panel works. This is a quantum mechanism. It uses something called the photoelectric effect, which was discovered by Albert Einstein. And that, by the way, requires the uncertainty principle for it to function. So your question, madam, the one you were asking, as to whether can you prove that there's uncertainty, I would put the question the opposite. Will there be a photoelectric effect without uncertainty? The answer is no. Now you observe photoelectric effect. So you have to find a way to understand it. And the only way to understand it is using the uncertainty principle. So you are caught. You understand what I'm saying? There's no choice but to accept the uncertainty principle. Because if you don't accept the uncertainty principle, how do you explain the photoelectric effect? You see, this is the whole point. There are a number of experiments which you're observing. You're making observations, so they are right. To understand them requires the uncertainty principle. So that's the answer to your question. But anyway, I was just going to talk about PV. It's a quantum mechanical process. Now, of course, we have perovskite, CIGS, all these are semiconductor nanomaterials. There are experts in the audience who work on that. They had beautiful posters yesterday at the university where we had our talks. So there are experts in the audience who can answer questions about these. All these are semiconductor nanomaterials. By nano, we're talking about 10 to the minus 9 meters, I think, right? Now, 10 to the minus 9 meters cannot be classical. Newton's law will not work at those dimensions. It just won't work. So I have to appeal to the laws of quantum mechanics to understand these materials and to use them to enable the sun to give me what I want. And all these, you're not going to believe this, but look at the lights here. They're all LED lights, light emitting diodes. How does anything emit light? Well, that you know. An atom goes from an excited state to a lower energy state. That's how light is emitted. It's the only way we know. That's a quantum process, isn't it? And that, to understand, requires quantum mechanics. So these LEDs up there are quantum devices. You have some things called BLDC fans. Now, in contrast, the AC fans, which most of you probably have in your homes, are not quantum devices. They are electrical devices. But the BLDC fan uses an SMPS switching, which again requires diodes and transistors and integrated circuits and microprocessors. So these are quantum devices. So now we don't talk about 100 years ago and ask, okay, is the uncertainty principle true? If it were not true, none of these devices would work. As simple as that. And you're using that every day of your life, and all of you have in your pockets mobile phones. How many transistors do you think are there in a mobile phone? Hang on, I'll come to your question. 1 million, 1 crore. Yes, please, your question.
Though, sir, Newton's laws worked up till a point. Until that point in time, sir, couldn't we have said that they're true?
No, it's not that
just
we did,
because.
Madam, you are there because of Newton's law. If Newton's law failed 100 years ago, you wouldn't be there, ma'am. I'm sorry. It's true, right? So up to a point in time, it's nothing. Yes, Newton's law has limitations, but not at our scale. I'm standing here because of Newton's law. But I'm also standing here because of quantum mechanics. Now that's a trick answer, which we can discuss on email because I have to leave. As Mr. Chairman, sir, is looking angrily at me, I have to carry on. I have to carry on. Now I have a list here of devices created by my friend Supriyo Datto in America. He's a professor at Purdue University. And he created these beautiful things which are absolutely based on quantum mechanics. I don't have time to go into them. Microprocessor chips are quantum mechanical. Maglev trains in China. Now they have trains in China which can run faster than jet planes. Okay? So you don't have to take a plane anymore. You can take a train. You reach. They use superconductivity, which is a quantum mechanical process. It's a fantastic, fascinating aspect of quantum mechanical many-body systems, superconductivity. Okay, all manners of electronic control uses quantum mechanics. All manners. So you see now, quantum mechanics is not something that you mug up and pass exams. But anyway, coming back to this, I don't think I have to. Well, I have raised some issues about, see, solar is now big in India, but in a wrong way. And I'm going to tell you what is the problem with grid-connected solar power. Why do you need localized systems? Why? I mean, I should tell you this story. I'm sorry. Give me 1 minute. I mean, I should be done in a minute or so. Yeah. I have to catch a flight, not you. I understand that. But I don't mind taking you with me. Yeah, okay. But anyway, you have this horrible thing that I visited in a college. Their whole rooftop was covered with solar panels. But I went in there and found that there was something called load shedding. There was no power inside. And then they had to turn on polluting diesel generators. That is the problem with the grid, you see. There may be a problem in the grid, near Kacheguda or wherever. And your rooftop panels are useless. They'll shut them off. So you can't use your sunshine. Okay? And I have listed some things. I don't want to get into that. But this is the kind of solution I'm proposing. We call it microsolar. And these are some of the advantages of this. It's actually very cheap to use and very nice. And yeah, I'll come to this. When you finish all these pictures, I'll have only pictures now to show you, because I doubt if any one of you have ever installed a solar panel. Have you? So you have not installed a solar panel, right?
I have installed.
Sir, you don't count. I'm asking them. Of course you have. I'm absolutely sure you have, but you don't count because I'm asking these youngsters, my little friends, my grandchildren, okay? And so let me tell you about a little program of training. This program had two aspects. None of these students knew English. So it was completely in Bengali. And none of these students had studied science. Okay? So it is that simple. How long did the program last? Well, 3-4 months, but that was because we were doing it once a week. So you can see that these are girls from a very modest economic background, minority background. You can see them from their dresses. And this man here is my friend Shekhar Banerjee, an absolute genius with no degree. So, and she's the director of the institute which ran this program. And you can see what they're doing. They're prepping a solar panel. So that's what I said. If you have not installed a solar panel, you wouldn't know what prepping it means. You have to prep it. You have to prepare it. And there are some technical things that you do. But it's very easy to do them. And now they're measuring voltages and currents. You know, these are geography students, history students, commerce students. But look, they're doing it. It can be done because science is for everybody. Now they're installing, for the first time in their lives, this is an LED bulb which they're lighting using a battery. And they're doing an LED panel. And this is, you can see yours truly. They have an LED panel showing giving of light. And the same thing here. This is fantastic. This is a BLDC fan, a brushless DC fan, which is being prepped by the students. Same thing. Now they're putting it up. How many of us have put up a fan in our homes? No, think of it. They're doing it. It can be done. We have an electrician from the local neighborhood to do it for us, and we pay that guy. But we don't do it ourselves, right? So they can do it. Now, one of the problems of solar is, of course, the question that always comes is what do we do when it's cloudy? And I'll end with this. Of course, when it's cloudy, the sunshine is not much there, but it's still light. And photovoltaics works on the presence of light. That's it. Now we have a more flexible approach to solar. It's not all or nothing. So we have AC-DC changeover switches. It can be used with batteries as well as with the grid power. So suppose your battery runs out because it was cloudy, you switch to AC. So the flexibility of these devices is very much there. However, there is a research problem. And the research problem is fantastic. It is that, what do this thing use? Now you will say, oh, it's using AC. No, sir, it's not using AC. These have drivers. All these LEDs have to have drivers because LED is a DC device. A diode is a DC device. So how do you use AC to run them? You have a driver. What is the output of the driver? It gets AC in, but the output of a driver is a very weird looking high frequency, high voltage signal. That's the driver is producing. We don't even know oscilloscope. I don't have access to a lab. I'm a theorist, unfortunately. And this is where I wished I had a lab, okay? But I've been talking to my institute experimentalists, so maybe we'll get there. So this is my last transparency, sir. I'm just saying, change to microsolar. Try to use your own sunshine for your own benefit, whatever you can afford. See, I'm using this shirt, right? Now, you don't know how many shirts I have at home. But if I want, during the next festival, I can buy another shirt. But will I buy 20 shirts? Efficiency of each shirt? I don't have to. I buy things according to my needs. So I live in a small house, I need less power. You may live in a big house, you'll need more power. I'll install a fewer panels than you. All the technology is available. So please, this is the time to use quantum mechanics to our advantage. Thank you very much indeed. I'll probably miss my plane, but it will be worth it. I'll take a few questions nevertheless. I have answered a couple of questions, but if there are any more, yes, please, over there.
Yeah. You can ask a question.
Yes, hi.
Besides the fossil fuel mafia, which is withholding us from using solar energy, are there any other reasons besides that?
Mostly that, I'm sorry.
It's mostly that?
It's mostly that.
Oh, okay.
Because solar in other countries are advancing very much, like China, for instance. We are behind them. China, even UK, which has a huge amount of oil in the North Sea, they're still refraining from mining it because of environmental concerns. So you have to use it. Okay?
So they're doing it only for their personal profit entirely?
Yes, it is. I'm so sorry. This is a political statement. I did not want to wish it. We did not wish to make it, but I'm sorry.
It's okay.
Yeah.
Sir, I have to have a question.
Yes, please.
Sir, not to offend you or anything, but can you tell me how this is?
You can't offend me. Come on.
Sir,
I'm
how
too
is
old to
this?
be offended, please.
Yeah, how is this interlinked to quantum mechanics?
Ah, okay. It's a good question. Let me answer that question in a word by saying that from top to bottom. There. I guess you missed this slide. Have a seat, please. You missed this slide because I went over it too fast. This is the basic mechanism of how a solar panel works. It uses something called photoelectric effect, which is a quantum mechanical effect. Take any book on quantum mechanics from your level to the most advanced level, they will discuss photoelectric effect. So that's where you begin with. It's a basic mechanism of a solar panel. And now, all these things I cited, they all use quantum mechanics. I was answering to some question here that if the uncertainty principle wasn't available, if it wasn't a principle, none of these devices would work. So that's how quantum mechanics is helping us on a daily basis, you see. And these are materials used to make solar panels. These devices which you use in your house, tube lights and bulbs, LED tube lights and LED bulbs, and BLDC fans, I don't know if you have any, they're all quantum mechanically operating devices. There's no, these won't work if you don't have uncertainty principle. And all this, I could not go over this list because I really have to rush. I mean, otherwise you talk to Indigo and tell them that this Buddha is whatever. Okay. Go ahead. Yeah. Sir,
there's one more thing.
Okay.
Solar panels.
No, listen to Sir. Sir is going to dictate who is going to ask a question because I have to rush. But you're free to write me an email, okay?
Okay.
My email is available here.
You ask your question.
All right, sir. So it costs a huge amount of revenue to maintain solar panels.
No. If you install a solar panel in your house, all you have to do is take a slightly damp piece of cloth, go up to the roof, wipe it. Maintenance, done.
Okay.
So this idea of very expensive use, wrong.
Last question.
So solar works, but my problem with microsolar is batteries. So we're
Battery.
going to move away from fossil fuel mafia to lithium ion mafia.
Excellent point. Battery is a bit of a problem, but you can make lithium ion batteries at home from the little pencil-shaped lithium ion batteries, which are sold again by China at an enormous amount of money. But let me finally give you this answer. It has to do with fundamental physics. All the electrical devices in physics uses the Faraday's law of electromagnetic induction. I think this statement is known to all of you. Yeah. Faraday's law of electromagnetic induction. But there's another law of electromagnetic induction, except it is not called a law of electromagnetic induction. This is when you interchange the electric and magnetic fields in Faraday's law. It was actually discovered by Faraday, but Maxwell put it into mathematical language because Faraday didn't know any math. There's a very beautiful story about Faraday I could tell you some other day. He didn't know any math, absolutely math illiterate. But this law is leading to a completely new class of motors. They're called electrostatic motors, but they're not electrostatics. They use this new law of induction. What is the great advantage? They don't need permanent magnets, and therefore, they don't need rare earths. This is happening. So there's a huge thing happening, okay? You have to join the adventure to help mankind, to help Mother Earth, okay? Yes, please. Oh, sorry, not you. You have asked a lot of questions, some other people. Yeah, please.
I think this is a common takeaway from this entire lecture. Thank you so much again for answering. What are the common stuff that I can do right now to change the situation?
Get a solar panel, which you can't really make at home, but you can buy it. You can buy a solar panel and then connect it. You have a study, I suppose, where you do your homework.
Yeah.
Connect it to a light in that thing. That's it. You're already saving Mother Earth. You're not turning on a switch, see?
Thank you.
Yeah?
All right.
One last question there.
You had said that even though they had many solar panels on their roof, they weren't able to use it. But if we aren't able to use them, what would be the next best source that we can create ourselves?
I went again, the speed with which I went over that. So when you have all these solar panels on the roof, if they are connected to the power grid extends all over Hyderabad, all over Secunderabad, right? So something happens maybe in the Hussain Sagar, near Hussain Sagar, they will shut off the grid. And then you are powerless. Even though the sun is shining and you have 1,000 solar panels on the top. It's useless. So microsolar, have your own solar power generating mechanism in your house. That's what I'm suggesting.
Thanks.
Thank you so much, sir, for such an inspiring talk. I'm sure students could learn a lot from this lecture.
No, please.
If you all have any queries, please contact him. The contact details have been displayed.
Very good. Sorry so much.
Okay. Yeah, before we move on to our next distinguished lecture, please note down contact details for Professor Soumitra Sen-Gupta as well. If you have any doubts, you can contact him. Okay, so now we move to our special board work distinguished lecture, especially designed for school students. And may I please invite Professor G. Manoj Kumar to introduce our speaker.
Good afternoon, everyone. I think if you count most luckiest person in the world today, they will be you, because today we have one of the finest minds which this country has produced, not only in terms of research, but also their finest teachers. Now we have Professor Jayant Kumar Bhattacharya ji, for a distinguished theoretical physicist. He works in theoretical areas. He obtained his PhD from University of Maryland, And after finishing the PhD, he worked as a faculty at several eminent institutes in the country: IIT Kanpur, IACS Kolkata, SN Bose National Center for Basic Sciences, and Harishchandra Research Institute. These are all top-notch institutes in the country which conduct both theoretical and experimental research. After superannuation, he further worked at IACS Kolkata and IIT Kanpur. Since 2025, he has been working at Harishchandra Research Institute as a visiting professor. His areas of interest are equilibrium and non-equilibrium statistical mechanics, critical phenomena, fluid mechanics, and different kinds of dynamics, both classical and quantum. Welcome you, sir, and good luck.
Thank you very much. All right. So the first point is, can you hear me at the back? Very good. All right. So my work has been made very easy by Soumitra, who was my colleague for several years, and he has more or less told you everything that needs to be known. I'll put a little more, in some places a little more flesh, and probably go into a couple of things which it was already, everything was implied in the talk, but in his talk, but something which would benefit from a different kind of retelling, let's say. So all right, what is the what's the primary difference between Newton's law from a more functional aspect? What is the primary difference between Newton's law and Schrödinger equation? Both were written down by Soumitra, and let me point out something which is trivial, but it makes some kind of sense, as you will see. So Newton's law, x double dot so oh, this is hardly coming out. Can you see at the back? This is as hard a chalk like as I have ever seen. Better now. So x double dot is force per unit mass. Let me call it this. And over here a function of x and x dot. So it's the acceleration, mass times the acceleration, which is the force. This force over here is the force per unit mass, so prevents me from writing an m. So all right. So this is what is what the dynamics is. What should be now? What does one mean by dynamics? I give you an initial condition, and dynamics means that I give you a set of laws by which, if I give you the initial condition, you will give me the condition at any future time. Put this way, it does not do it. I have to give you an initial condition about the state of the particle. Now, this does not play that game where I have to write it. If I want to have that facility, then I have to break this up into x dot equal to p and p dot, which is m times x dot is equal to p dot is equal to f of x and p. Now you see it has to be two first order. This first order differential equation can be written as the second order differential equation is two first order differential equations, and now life is much more transparent. At t equal to 0, x0 and p0 are given, and given x0 at these two first order equations will take you to the future evolution. So the way you understand time evolution of a dynamics is that you write down a set of first order equations, and the set of what classical mechanics in one dimension requires is a set of two equations, one which tells you that x dot is equal to p. The two variables. So why? Because what is the state of the particle? What if I tell you that I need to know the state of a particle in classical mechanics, what that means is that I want to know the x and p, and if necessary the x and px, y, py, and in the worst possible scenario all three of them. But that is three sets. So two each for every dimension, and that's the maximum that you can have. So state, the state of a particle is the initial condition given which you can talk about the evolution of the thing, because the evolution is given by x dot equal to p and p dot equal to f of xp. So dynamics always is initial condition is given, t equal to 0 given, and you have to find at any t what is the state. Now all right, you can say that what else could have been done? Well, I don't know about elementary textbooks now, which you would be knowing much better, but we grew up with mechanics of this variety being taught by saying that you see one had to use these relations like x equal to ut plus half a t square and things like that, which comes from integrating the free particle equation. So the point was that one was told in school that if somebody gives you two t's and at those two t's the corresponding x's, that is a fair thing to do. So it is possible to track the dynamics by giving you two x's at two t's. That was something very common that at least my generation learnt in school, and that is what you are not supposed to do. Dynamics is that give the state at the initial time. I know the state. If I want to know that, if I give you the state at t equal to 0 and t equal to 10, I know the dynamics. Otherwise, how did I know t equal to 10? So knowing the dynamics means that I know it at t equal to 0, and then I would like knowing the state, and then I would let the state evolve, it will be evolving according to x dot equal to p and p dot equal to the force. So that would be the two set of first order equations, give initial conditions for x0 and p0, and that's done. So this is classical dynamics in one dimension. In two dimensions, you would have y and z going along with this. It would be x dot px, and then you would have to put this, and then it would not only be, it could be a function of x, y, z and px, py, pz, and so on down the line. So increasing the number of spatial dimensions is a matter of bookkeeping rather than anything which is particularly useful. I have already heard a lot in the first lecture. It actually takes up does a lot of the initial stuff for me, and therefore this should be quite trivial for you to go through. What I have to say should appear trivial. That's the, so all right. Now this is what the state is. This is the state, which is the initial condition, which is a set of x1, x2, x3 and the corresponding p1, p2, p3. So that is x, y, z and the x, y, z, px, py, pz. Better to write, easier to write it as x1, x2, x3 and p1, p2. So that. Now comes the question that, all right, this is the, but this whole business of Newtonian dynamics got sort of, this is Newton, and as you heard in the first lecture, this whole thing got a little sort of, let's say, required some kind of a modification when one went into number one. So what were the sequences that, I'll put it in some kind of a sequence. Problems began with Planck in 1900, when Planck had to say that this sunlight that we are seeing, so Planck's problem was with the sunlight, and what he was not being able to properly account for is the 1913. That's another, it's something which is once again quite difficult to imagine how Bohr ever could, make a statement of that kind. It's the logic of it, I would never be able to tell you, but the point was that he was immensely successful. The spectra which people saw of these elements, this was not understandable unless one made the statements that Bohr made, which essentially was that moving around which has protons and neutrons. So protons and neutrons all right. So 1913 and then in many ways, and next thing is the Compton effect. And when did I start? At what time did I start? I have 15 minutes. plus 5. I will discuss it.
Yeah, 15 minutes after the discussion.
All right. So Bohr following Bohr comes this Compton effect, which with this 10 plus 5 I am going to drop, and so we that what does one, where does one, the next step is really the big one, because now you are going to the next comes the stage where all these are things which are saying that classical physics is not exactly applicable. So it is something which classical physics would not have given you. The part of the Planck spectrum, classical physics was good for a certain part of the spectrum, but does not work in the high, where it is this low temperature limit, and then there is the this is of course always correct, and then comes Bohr, where the details as the spectroscopy gets better and better, the details can be missing. So there is something wrong, something not going on right. And then comes there is Compton effect, which does this another scattering experiment, and which I'll skip. But in the history of all this, the Compton, it is important to follow the logic which went along over there. So there was this Compton effect, where once again it seemed like it is having light as a particle would be a decent thing to, it would be the right thing to talk about. And then all of a sudden comes 1926, and the part where this is, I never really, I can't say I understand why it was written down, but Schrödinger changed the whole nature of things. That the basic point which I started with was Newton's law, which required, which was a state which required two variables. What Schrödinger did was change the nature of the state. The point was that in between comes why was he for, so all that I'll focus on is why did he want to change the nature of the state. This had to do with the fact that the place where all the so-called classical physics, all these changes which were from classical physics were going on at dimensions which were incredibly small. So you were looking at length scales L which were less than or much less than 10 to the power minus 8 centimeters. So you were looking on a scale which was unimaginably small. And at that unimaginably small scale, the point was that it seemed that the dynamics is not quite that of the dynamics with which we are familiar in the everyday setup. And now if that is not the dynamics, then the state, which was the vital thing that we started out with, state determined by x and p makes no sense. So state determined by x and p, and also Heisenberg was to come somewhat later, slightly later, but all more or less at the same time. But the point is that state x and p did not make any sense, and that would not be, and therefore what Schrödinger wanted to talk about, and was a probability distribution. Probability distribution coming from the fact that the act of measurement can change the state. See, it's an electron and you are shining light on it, and you are trying to get its state by shining light, but that light is going to be, the electron responds to that light and just changes its its Newtonian parameters, let's say. So there would have to be, it would, and therefore the point was that this measurement process, if things get smaller and smaller, that if I'm talking about this 10 to the power minus 8 centimeters and round that, it is not a deterministic dynamics that I would be aiming for. So the big thing about Schrödinger was that change the state. This is not getting the x and p at the same time, is not a practical way, and also not the right maths. Those unfolded later a little bit, but the fact that this x and p state did not make sense. The measurement, it was very susceptible to measurement, and therefore pinning it down was extremely problematic, and therefore you can define the state. The state according to Schrödinger would be a function psi of x, a psi of x which in general will be a complex valued function. It's a complex valued function. It is not required to be a real valued function. So the state is defined by a psi of x with the physical interpretation that psi x mod square is the probability of finding the particle between x and x plus dx. So he introduces the variable with which to track the particle as this function psi of x, whose magnitude, the mod square, is the probability of finding it between x and x plus dx. Now he has to write down an equation. So now it is the psi of x. The psi of x has to be in general a psi of x and t, because the state of the particle will change with time, and it is all going to be determined by psi of x and t. If that is the only thing that is going to determine, the time dependence can only be a del del t, because the question that I will ask of you is that given the state at t equal to 0, what will be the state at a later time? And this question can only be answered if it is a first order equation in t. You get the point that we are talking about differential equations and when it was Newton's law with d2x dt square equal to f of x and t and p, xp and t. So d2x dt square and there, but now we have a question of a first order. I have a psi of x. Given the psi of x, at t equal to 0, I want to know the psi of x at a later time. Over here, I had two variables, x and p, which are sort of, they make up a state, and why they make up a state and so on, one can talk about that quite a bit, but it is a sort of conjugate the way the classical mechanics developed and so on and so forth. The x and p were absolutely related, which is essentially what you can see in the, if you write down the the Hamiltonian, and write the equation as equations of motion as del h del p and p dot equal to minus del h del x. So that was the natural evolution over here. The natural evolution over here has got to be a first order equation. Over here it is second order, as you can see, two equations in first order, so it's a second order equation. But over here I have to write a del psi del t over here. So del psi del t equal to what? Equal to, now you will look for the right hand side, and what Schrödinger came up with, the only thing that could make sense is writing the energy operator here times psi. It made sense because he tried out a few simple situations and found that worked. We don't have time for that. And so making it dimensionally correct, it is I h del psi del t is equal to h psi, where this h is p square over 2m plus v of x. Let's say if it is d equal to 1. But what is this p? This cannot be the momentum that we have been talking about, but then it should have been Newton's law form, that x dot equal to p and p dot equal to x. So this p, which is the momentum over here, has to be something which is related to the kinetic energy in some way, and but not quite, not operationally writable in this way. It is h equal to, let me try to make it clear. It is h equal to p square over 2m, but what are you going to write it as? You are in the business of doing quantum mechanics. With this, h is like the energy. So for energy, you have written IH essentially, if that is the form of your evolution equation, then essentially for H, you have written IH del del T. So now for P, you have to do something for the P over here. So that P over here, now you worry about that, look, I mean, what is going to be the correspondence between the t and x? What kind of a x derivative that are we going to answer comes out as a x squared, because there is a classical thing, this process of diffusion, particles going out in diffusing away in various directions, where the equation of motion is del phi del t equal to diffusion coefficient times del square phi. So when things are sort of diffusing out, that's a quantity, a sort of hazy description of things, then it seems like that del phi del t d del square phi is a good thing to do, in which case that if you take over into this quantum particle, which has a kind of blurred existence, then you would be writing, then you would be taking over this P as being IH. That's dimensionally, and yeah, I am also through. So that is dimensionally correct, and the I is required to give you this balance certain other things which we don't have the time for now. But I put it in this P over here, and then I have this H becomes. Then this H becomes, it's P square over 2m, so it is minus H bar square over 2m del 2 del x square plus V of x. So that's the energy of the system. And the energy of the system is like del psi delta, del psi del t. And therefore, you put these two together, make it dimensionally consistent, and what you end up with is I H del psi del t. These are essentially getting at del x square of psi plus V of x. So that on psi. So that is what is Schrödinger equation in one dimension. And if it is two dimensions, you put a del x square plus del y square. If it's in three dimensions, you add a third. That is, in general, it is this operator del square, which is del x square in 1D, del x square plus del, and so on. But that is a sort of logic which leads you to the Schrödinger equation, and the rest of the game is that you take systems which are, you start with simple systems like a single particle enclosed in a box, and then an oscillator and this and that, and work it out and see what the energy levels are going to come out as. And it works, you get the energy levels, you get the experimental measurement comes through the light that is emitted, the wavelength of the light, and so on and so forth, and you get a credible, what Bohr had managed to get through some not so clear argument is here obtained on the basis of far more constructive logic, and that's where this is a good point to stop. Any questions?
What is the
I request everyone to please be seated. We'll be finishing this session within 5 minutes.
what is the significance of the I in the equation, sir?
Oh, the significance of the I. If you did not have, sit down, sit down. This is the way the math goes. You see, I brought in the diffusion equation, and the point would be that if I did not, forget about, look at this final thing. Suppose I did not have any potential, free particle, and then if I did not have the I over here, what you are going to look at is this sign is not quite, it makes it weird, but suppose, I mean, the sign was right, then what you would, if it had a plus sign, it would make a diffusion equation which you don't want, because it is not a set of the quantum particle is not diffusing away. So you don't, if you say that it is what about this minus sign over here? It's a tricky argument. The minus sign is required by the fact that this P has to be the right kind of, these are actually operations which are taking place on this scalar function psi, and you have to be the thing which you want is the P square over here, and P is what is of the order of h in for small particles, quantum for which quantum physics is valid. So P would have to go with h bar over here, and if you now put I to it, then you make it go away from the diffusion equation and allows it to support a kind of wave equation. Not fully, but kind of. Why kind of? Now, a wave equation will have to be periodic. A wave would have to be periodic in time. So you take a solution which is like e to the power I omega t, and so it is this e to the power I omega t, which when you put it over here, it becomes takes into account this minus sign, and so you write it as e to the power I omega t phi, and you get rid of this I over here with a minus sign, and you have a del phi del t, and over here it is just the phi with the phi, this part acts on the phi over here, and this over here has become a minus with phi over here. Forget this is all free particle, and you have a nice kind of diffusion equation if you do that. So it is this question of, you don't want a diffusion equation. What you want is the equation where this particle is going to sort of stay confined, probably oscillate if you confine it in a small region, and so on. And that is ensured by essentially having the minus sign. That's the other. Otherwise, it becomes in that limited diffusion.
Okay, thank you so much, Professor, for the wonderful and engaging talk. May I request Dr. Ramachandra Rao Yalla to kindly present a memento to Professor M. Ghanshyam Krishna as a token for our appreciation to efficiently carry the session. Yeah. May I please invite our in-charge Dean, School of Physics, to finally give concluding remarks.
Okay, the crowd has become half. It's very good. That is what quantum mechanics is supposed to do. So we have achieved our goal. Anyway, jokes apart. Anyway, thanks for attending the sessions, and as you can see, most of the speakers were trying to pitch it at a level that they thought is palatable, or kind of at least is easier on your part to kind of at least start following it. But I'm sure you have picked up some language, some terminologies, and a broad sense of where things are going. And especially with Professor Partha Majumdar's talk, you also understand now that all the things that you are using on a day-to-day basis has an implicit quantum mechanics involved in that one. So these are the things that you have to kind of take home message, and it may look slightly crazy, non-intuitive, and doesn't follow the realistic physics that we have been taught, but that is what it is supposed to do. So basic idea is that there are things that we don't understand at this point of time, and these are beyond our reach, as many of the speakers also mentioned. So these are the things that you keep in mind, and then take home and lower it, and decide if you want to continue physics. And we would love if you come back and join us for your higher education, and then it will be a fun time for all of us, right? So with those few words, I'll say thanks for coming, and any opportunities you see is possible, you do drop in a message, mail to Dean's account and interact with us. And of course, if you have any questions on the talks that were given, you should put in an effort to send those questions to the speakers, and then they all promise that they will respond. So you should make use of these opportunities that has been given, and thanks to the teachers and the school managements to have sent their students to participate in this program, so that it becomes a kind of a full house grand success program. Thanks a lot.
Thank you, sir. May I now invite Dr. Abhiram Suri to give word of thanks.
It's my privilege to give vote of thanks in this very prestigious conference with distinguished speakers. I thank our Vice Chancellor, Professor B.J. Rao, IOE Director, Professor Ghansham Krishna, the Dean, Professor P.K. Suresh, our in-charge Dean, Professor Nirmal Kumar Vishwanathan, and all the office staff of School of Physics, and all the volunteers for having helped us in organizing this conference successfully. And also I would like to thank the University Guest House staff and Mr. Das, caterer at Tagore Guest House, Public Relations Office, security personnel for their efficient support, warm hospitality and smooth coordination. And yes, if I have left anyone in this vote of thanks, I beg your pardon. Okay, with this I would like to end my vote of thanks. And there is an announcement. One thing is that there is high tea for all the participants. Please go and have tea. And also all the participants will get participation certificates. Please collect it from the registration desk. Thank you very much.
Okay, so thank you so much for your enthusiastic participation, and we wish the students every success in their scientific journeys. Please join for photo session and high tea outside. Thank you.